Hello and welcome to the show. My name's Relevant, and this is Do All the Things. On today's episode, what is this strange little amplifier? Stick around and find out. The short answer is it's the first amplifier ever built. The long answer is, once upon a time, back in the day in high schools where they taught us actual skills, they would have had an electronics class. And back in the days when schools had actual budgets to teach us actual skills, they had kits for the students to build. And that's exactly what this is. This thing probably is dated back to the 50s or 60s, and it was a kit they would have given you in high school to learn how to build a tube amplifier. Now, of course, this thing is not stock. It's been heavily modified over the years, but hey, where was I going with that anecdote? At any rate, when I was in high school, they had in the communications tech class that I was in, some leftover stuff from the old days. And there was one of these kits that I found digging around their archives. A teacher like me let me do some things like that. Hey, can I put it together? Yeah, and I got graded on it. The kit was complete except for tubes. I had to go and find tubes for it, and that's when I discovered tubestore.com and have been buying tubes from them ever since. At any rate, these aren't the original transformers. This isn't the original tube configuration. It originally had a 12AX7, a 6BQ5, no, a 6AQ5 power tube, and a 6X4 rectifier. It had this smaller black power transformer and this much smaller output transformer. These transformers were some leftover weird ones that I found at an electronics supply shop in their old archives. They're standard television products, branded, labeled, if you can kind of see the side. What it is now is something that, according to my records, I call the Oddball SE 4.1. And this is the schematic for it. I called it Oddball because the challenge was I was making amplifiers using oddball tubes that I had kicking around. And some of these tubes in this case, well, EF84 isn't exactly oddball other than the fact that I had no other amps that really used it. That is an EF86. It's a pentode preamp tube. That's still, you can still get those, but still, it was different. Right there, a 6X4, it's a tube rectifier. And then this guy right here is a 6AL5. What's a 6AL5? It's a diode. That's it. It's just a tube diode. And what's this tube diode doing? Well, for such a low wattage amp, it wasn't good enough for me to just cathode bias it. You can see the output tube right there is just tied directly to ground. I actually, if you recognize what's going on here, built a little negative bias circuit for this thing. This tube is negative biased. And instead of using a diode, I used a tube. So we have a tube diode running the bias circuit. It's really quite absurd. And it does work. Let's plug it in. So the funny thing about this, guys, it's completely a clean amp, not necessarily by choice. You see, the EF86 on its own doesn't have enough drive for the power tube. It has enough to make it work, but not enough to get loud. So pretty much I can crank this all the way out and that's as loud as it's getting. Now cranked out, bright dark doesn't do much. Bright dark is just your typical bright cap across the volume knob. We have a very basic tone circuit, even though I don't know that the 0047 I used is necessarily the right value. Really? Oh yeah, it does do something. And then there's a high-low switch on the EF86, theoretically changing its bias. But looking at this, we go from 4K with a 1U cathode bypass to, I guess it would be, a half a K, 500 ohms. Doesn't seem to make a whole heck of a lot of difference. It's so subtle. Some of this I did for the lulz, not exactly knowing what to expect. Funny thing is, it does sound and feel good. Having an EF86 on that first preamp stage directly connected to your guitar just... It has a nice feel when you're playing it. It has a nice feel. Now, mind you, it probably helps that the volume's completely cranked. So what are we gonna do with this amp today? Well, first, I wanna run some tests on it today that I didn't know how to do back then. I want to find out what the resistance of this output transformer is. I want to find out what the current capacity of this power transformer is. I want to switch the output tube back to cathode bias because I actually bought some tubes that will work in this amp, but they won't work in this amp as it is. Riding that Russian surplus wave, I acquired these guys. That's a 6N43P or a 6P43PE, something like that. It's similar to an EL84 and it's a 12 watt rated tube and its pinout is exactly the same as the EL84. I can literally drop it in there, but it doesn't work. Half because it gets screwed up by the negative bias. The negative bias is set up for this tube and it is not accommodating to this tube. I did do an experiment where I disabled the negative bias and put cathode bias, and then, hey, this guy started working just perfectly fine. So I want to make this more universal so I can pop these kinds of tubes in there. That means I'm going to be losing the little 6AL5, but I have other plans for that because there are 7-pin triodes. I think I have one in stock. Maybe we can add an intermediate driver tube between the preamp and the power section to get more volume out of this thing. So I gotta start by pulling out these tubes because for the experiments I'm about to do, we don't need no tubes. We'll start off with the simplest experiment, finding out what that output transformer is. All right, in order to test an output transformer, we need some source of low voltage AC power. Here's a little something tool I put together. That's just gonna give me 12 volts AC right here. We kind of need a dummy jack. We're gonna need not one, or you know, we can do it with one multimeter. Yeah, we'll do it with one multimeter, but you need a multimeter, you need a calculator, and we probably need like, actually no, that should do. Well, we need to prop this up so you guys can see it. That's an important part of the recipe, isn't it? Also want to make sure it's stable because we're going to start dealing in voltages here. Want to make sure it's safe. All right, so we got to plug something into the speaker jack. That's going to make sure we lift the speaker connection from ground, even though that feature isn't here. And we want to mind all our connections because we're trying to disconnect it from all the general circuits. So we're gonna end up charging power here and charging power. Okay, yeah, so with the power tube removed, we've lifted the secondary connection. Now we gotta get our source of vitamin AC going here. And then we want to get our multimeter ready. We're gonna set it to AC and we're gonna set it lower to like 20 volts right now. We want to connect it to our test leads here so that we can get a voltage. Oh, 12.22 volts. Now we will connect it to the speaker output and check for voltage drop. 12.17. Might want to write that down. All right, it's sagged to 12.16. For our purposes, that's close enough. But we want to switch our voltages now while leaving the speaker connected to, you know, an upper range. I'm going to 2000 volts here because we could get well over 200 volts. And now we're going to connect our multimeter to the output transformer primary. One of them's on the tube there and one of them's on the B plus connection. Oh, 133 volts. This is the information that we need. Once you got this information, the math is really quite simple. We take these two voltages and divide them to get a general ratio. So we're going 133 divided by 12.1. We get a number of 1094. We got to take this 1094 number and we got to multiply it by itself. That's squaring it. On the calculator, that's as easy as taking the number you just got, putting in memory, press memory plus, then hit times memory recall equal, boom. We got a new magic number of 119.63. That's our magic number. Why is that the magic number? Because we simply take that magic number, multiply it by 8 ohms, and oh, we have a transformer load of 957. So that's almost 1K, which is actually nowhere close to near what we need for this amp design. Back then, I just kind of YOLO'd stuff together. I didn't actually know the math and engineering of what I was doing. Makes me wonder what the heck was this transformer rated for? 957 at 8 ohms. We can divide that by 8, get our magic number back, go multiplied by 16. We get 2K at 16 ohms. This was either designed to drive a line load. That's what I think it is. If we take our magic number and multiply that by something like, let's say 600 ohms. Oh, look at that. We get 7K. Now everything's starting to make sense. That transformer's a line driver. I should probably replace this transformer in this revision. I have some other scrap single-ended transformers we can use. But first, I want to test the output capacity of this particular power transformer. We're not going to need our specialty tool here for this. That's for testing yada yadas. Okay, so for this operation, we're going to exploit Ohm's law. Exploit Ohm's law. But the first thing we need to do is find out what voltages this transformer actually runs at. It says 325 on the side of it, but you know, that could mean anything, knowing me back then. So plugging the amps in, powers it up. Again, we have no tubes on it. We're gonna find those 2 secondaries coming off the transformer. One of them's right there, and this is tricky because one's slip, the other one's right dear. And we're getting 664 volts AC. That's total, not including the center tap. So let's just write that down. Oh, 664, neighbor of the beast. Yeah, keep your friends close, your enemies closer, am I right? So 664 divided by 2 is 332. So I guess it was close to 325. I guess that was under load. I measured that. Now, one rough and dirty number I used to figure out what it's going to give me after rectification, which actually doesn't apply to tube rectifiers, but you know, just for the sake of argument, multiply that by 1.35. 450 volts. This thing's capable of almost 450 volts. So back to the exploitations of the Ohm's law. We are going to be using these 100 watt power resistors that I got. They're 1K each. And I actually plan on building a kind of load testing box because these guys need heat sinking to work properly. They'll burn up if you just use them raw dog. For the meantime, I just bolted them to the side of this broken hard drive. This aluminum chassis should have enough thermal capacity for this, and it's also gonna give it a nice solid platform to hold them while I do this experiment. So we're gonna need to go get ourselves some clippy clip test leads here. And we're gonna have to go and set up our meter to test amperage. This meter's good for 2000 milliamps, which I don't believe I should be exceeding that capacity here. Now, Ohm's law dictates, if I go and I grab the 664 number that we got, and I divide that by 2000 ohms, it's going to try to pull 332 milliamps out of this transformer, which I doubt it's gonna be rated for, but that's gonna put us right where we wanna be to kind of max out the power draw on this transformer and see what it's gonna do. We might actually want more, you know, more resistance than that once we kind of know where it's gonna sit, because we also gotta watch its voltage drop. That's gonna tell us whether the transformer's getting overloaded or not. But I feel like that's a safe starting bet. Now I plan on putting these 2 little resistors in series, much like this, and then one of them is gonna connect to one side of the primary, and actually we're gonna need a second meter for this, because we do want to track the voltage that we're gonna get. So if wanting to track our voltage, we're gonna clip it onto the actual 2 points on the resistor. That's gonna see our full voltage. And then we will get a test lead on the other side of the resistor here. Are we ready to do this? Oh boy, yes, we are. All right, let's grab a secondary here, and let's grab another secondary. Oi! That's kind of as expected. We're putting a load on this thing. We're down to 273 volts at 200 milliamps. So 273 volt drop from 600 means, yeah, we were overloading this guy. 200 milliamps though, that's potential. What could this be rated under normal circumstances? Because that test point there is going to yield 660. Now this doesn't actually compensate for the full wave rectification we're going to get. So we might want to test it again off the DC power supply, which actually might make a little bit more sense if it wasn't for the fact that we probably overload that tube. Now, bearing this in mind, that 1K might be too much, I actually ordered 3 of these resistors. So let's slap another one on there. Let's get 3K load on there. We'll just go ahead and shmoo that goo with a little bit of thermal and just 632 that pupper into place. This is also proof of concepting my load box because it might not have quite enough resistance to do bigger transformers properly. Sure. One there, jump her over to the next guy. Get another test lead, jump her over to the next guy. Let's make sure that these leads aren't touching the chassis of this hard drive. So 3K now, 664 volts divided by 3000 ohm. It's gonna try to pull 200 milliamps. Maybe that'll be more palatable to this transformer. Here we go. Less spark this time. All right, we're sagging to 340 volts. Still, again, 200 milliamps. The good news is these power resistors are barely breaking a sweat. The bad news is I had the camera zoomed in too far for you to see the numbers, but you can take my word for it. So I suppose if I knew more about this and knew how to do the math, I could determine exactly, what these numbers mean. We're getting a 50% drop here in voltage at a 3K load. I have no more of these resistors, so I can't go up to 6K. But maybe we can kind of, half things down. Let us look for the center tap. Oh, there it is. Connected to speaker ground. So in theory, if I grab right here, we're getting 244 volts off the center tap, 60 milliamps. 60 milliamps. Now 243 volts, that's more in line with a proper voltage drop coming down from the half of 332. Still says it's putting a fair load on there, and we're only pulling from one side of the secondary. So we're not necessarily getting the accurate representation. We're just basically getting ourselves, in the neighborhood. I'm gonna go down to 2K, 214 volts, 80 milliamps. So I guess we're getting roughly half what we were getting on the other thing. I almost feel like this transformer without voltage drop is going to be somewhere in the range of 80 to 100 milliamps, which you could actually do some good things with. I want to go online here and I want to find out 6x4 data sheet. Okay, well, it's rated for like 210 milliamps. Typical operation, 70 milliamps. Actually, the 6x4 might match decently with that transformer. I'm gonna pop that rectifier tube in place and we'll see if we can load test with the power supply. And this ground point here is a reasonable place to grab half of our power. We will do a voltage test now, sir. B plus being right about over here and ground that out. Now we have to switch to our DC. 400 volts DC. So if we take 400 volts, divide that by our 3000 ohms, it's going to try to pull 133 milliamps. So that will be within the max realm of our rectifier. So we'll set this popper up to be 3K, put some power onto here, and then we'll go grab a bit of B plus and see what happens. We went down to 275 volts, but I did not get a current reading. Oh, our meter was set to AC. No wonder we're not getting an accurate reading. 70 milliamps with a voltage drop of 223. Okay, well, I think we have a good general idea of what the capacity of this transformer is. It's getting significant voltage drop, like 50%, with only a 50 milliamp, or was it 60? Yeah, 60 milliamps of current draw. So I guess that transformer doesn't have much chooch going for it. We need about 30 milliamps to run that power tube, but not much more than that. So I guess that power transformer is just going to be just perfect for this setup. We might as well leave it there. Mind you, we also have the idea that the rectifier tube could be what's sagging. Oh, should we take this to the next level, sir? Should we? I don't feel like setting up a rectifier. Fine, set up a proper rectifier. Here's a 6 amp bridge. We shouldn't be able to overload and get voltage drop off a 6 amp bridge. We will connect test leads to the two AC positions. We will clip those, and we're not going to be running any capacitance for this, but we will clip those. I should pull out that rectifier tube. We will clip those onto those two output points. Turn the amp on. Now, silicon rectification connected to the positive. So what are we going to get here? 214 volts, 60 milliamps. We're regulating to 300 volts with no capacitance. Then we load it. It drops like almost 100 volts, 60 milliamps. 50, 60 milliamps. We'll call it good. Okay, so one of the first things that I want to concern myself with is the changing out of that output transformer. That load is not going to do. I guess it kind of did do, but if I start pumping more power through it, we need to keep those tubes under control. This is the original transformer. So how about we find out what its K rating, which is supposedly for a 6AQ5, is going to be. It only has like one set secondaries, primaries, no real taps. All right, let's load this pupper up and see what we got here. Oh, we're sagging down to we'll call it 8.87. Okay, we'll call it 8.87, 8.86. What's the output from the primaries going to be? 220. 220 by 8.86. Let's do some maths. 220 divided by 8.86. That's 24.83. Magic number is 61656. Multiplied by an 8 ohm load, 5K at 8 ohms. That makes a lot more sense. And sometimes I might use a 16 ohm cab. So times 16 ohms, 10K at 16 ohms, which is even more appropriate for what we're going to be doing with this guy. 5K should be fine for one individual tube. Yeah, that would be like a 10K load if we were push-pull. So yeah, that's great. Now, just for the sake of argument, maybe we wanted to get fancier than this guy. Something that looks a little bit bigger. Here's a vintage Hammond 91K. Came even in the box, but 91K doesn't mean anything other than a model number. Arbitrary. So let's tap on to the secondaries here. See what voltage drop we're gonna get. 12.08. So what's on our primaries? 132 by 12.08. That doesn't sound promising already. That's a magic number of 119.4 times 8 ohms. Go figure. That's about 1K at 8 ohms. So this guy is pretty much identical to the standard television products transformer that's on there, and it is likely a line driver. Or I think they're sometimes called like television scan transformers. They're for old TVs and crap like that, these transformers I found. They can, in a pinch, be used as output transformers. Well, they are output transformers, just not necessarily for a speaker load. All right, firing up the seat gun. Let us get transformer der origin mounted back in here. We also can't be sure of our phasing. Oh good, all the connections are at the top. That's coming right out. Yeah, hopefully there's no more zaps in here. I put drain capacitors in my designs, so there shouldn't be. Except I think we're just spinning out. Oh, you! I have a perfect size mini wrench for this. I don't know that I'm going to be using this ground point anymore in the new design. Yeah, this guy likes to roll around on me. Haha, Transformer, you served me well. But you are from a time when I did not know what I was doing. You are being retired. In favor of the guy who is proper. Alright, now I want to move this ground lug like right here to make it more cathode accessible, because the cathode's here, the ground lug was over there, it's mounted here, like, duh. The grounding scheme on this is just very quick and dirty. It's just like, oh, wherever I can bind it to the chassis, I just kind of chucked a ground on there. Alright, so red to B+. Which pin here was the hookup? I'm gonna have to look up the specifications. The anode's pin 7. That's the one I thought it was. Don't expect me to remember this all off the top of my head. I barely work with the L84s, but let's just get these speaker lines connected. I don't know why I bother still using these binding posts, like,